Okay guys, so in this video I want us to explore exponents and their properties. Now before we get into what the properties of exponents are and how to use them, I wanted us to first explore how to even get to them, and in that way maybe even make sense of what they mean and what they say. Now what we're going to do is just a relatively quick and informal discovery of the properties, because in reality these properties were discovered throughout hundreds and hundreds of years by different people throughout the centuries. You know, one person might have discovered one of the properties, another mathematician might have discovered another one, and then another one might have figured out how to write them and codifying everything, and then others might have formally proved those properties. And all of this happened throughout hundreds and hundreds of years. So what we're going to do right now is just a quick exploration of these properties. And I think the best way to start talking about the properties of exponents is by talking about the definition of exponents. Exponents are a way of representing repeated multiplication. And that's where we have to start. Exponents are repeated multiplication. So let's write down an example, and then we can start playing around with the exponents and see where that playing around leads. So we said that exponents are a way of representing repeated multiplication. So as our beginning example, let's just think about a to the 7th power. Well, a to the 7th power is a multiplied by itself 7 times. So let's write that down. A times a times a times a times a times a times a. So here we have a multiplied by itself 7 times. And we can rewrite that whole expression as a to the 7th power, because that's what exponents mean. It means how many times you're multiplying the base by itself. Okay, great. So we're starting with this definition of exponents, and now let's just play around with this. So the first thing I want us to do is to just see what happens if we multiply a base raised to a power by the same base raised to another power. So for example, what is a squared times a to the 5th? So let's see what this means. Well, we know that a squared is a multiplied by itself 2 times. That's what the squared means. And a to the 5th power is a multiplied by itself 5 times. So let's write that down. A multiplied by itself 5 times. And we're multiplying these two expressions. Well, if we look at that, that's exactly what we have written up top. This is a multiplied by itself 7 times. So we can actually rewrite this as a to the 7th power, just like we had at the beginning. Okay, interesting. Well, let's try out another example. What is, let's say, a cubed times a to the 4th power? Okay, well, a cubed is the same thing as a multiplied by itself 3 times. So that's a times a times a. And a to the 4th power is a multiplied by itself 4 times. So let's write that down. A times a times a times a 4 times. And we're supposed to be multiplying these two because that's what the original expression says. So let's multiply all these, and well, look at that. We have a multiplied by itself 7 times. So again, we could rewrite this as a to the 7th again. And we can just try out a third example just for the fun of it. Let's use a cubed times a to the 6th power. And again, we know what this means. a cubed is a multiplied by itself 3 times, and a to the 6th is a multiplied by itself 6 times. If we multiply all this together, we end up with a multiplying itself 9 times, which can be written as a to the 9th power. Okay, well, we can continue looking at different examples, using different exponents, and in the end, we would be able to, just count how many times we have the a, and that's what our exponent would be. But is there a faster way of doing this instead of writing all of these a's down? Like, what if we had a to the 15th power, a to the 15th power times a to the 50th power? It would be really annoying and very time consuming to have to write down all of those a's and then count how many we have. So here is where, we try to see if we can find some patterns. And hopefully with a little bit of thinking, you start realizing, well, wait a minute. In our first example, we had a squared multiplied by a to the 5th power. So we had 2 a's being multiplied by 5 a's. Okay, well, if we're just trying to count how many a's we have, isn't that the same thing as just adding together the exponents? And the answer is yes. Look at this. If we add 2 plus 5, that would give us a to the 7th. If we do the same thing with the second example, if we add 3 and 4, well, that also gives us 7. And again, these exponents are telling us how many times the a is multiplying itself. So a cubed is a times a times a, and a to the 4th is a multiplied by itself 4 times. So the exponents are actually telling us how many times the a is multiplying itself. So again, in our third example, we could add 3 and 6 to see how many a's we have. And that would give us a to the 9th. And finally, for this example that would have been annoying if we had to write out all the a's, now we can just add the exponents. A to the 15th times a to the 50th power would be the same thing as a to the 15th plus 50, which is a to the power of 65. And we didn't have to write down all of the a's, nor did we have to count how many a's we have, because we noticed the pattern. And this is exactly what mathematicians noticed. They noticed that if you are multiplying the same base to different powers, or it could be the same powers, but if you're multiplying the same base, you can figure out the final exponent by just adding together the individual exponents. So that's how one of the properties of exponents came about. In fact, it's called the product property. And the product property can be written with any variables that you want, but in essence, they will all say the same thing. The product property says that if you multiply a base to a power times that same base to a power, that would be the same as the base raised to the sum of the two exponents, or however many exponents you have, really, because even if you have 3 different bases multiplying each other, like in this example, well, in the end, we could follow the same process a multiplied by itself twice times a multiplied by itself 3 times times a multiplied by itself 4 times. And that would still be the sum of all the exponents, which in this case would be 9. So that is the product property, and that's one way in which you could discover it. Just understanding the definition of exponents and playing around with it, you would get the product property. Okay, well, let's keep playing around. Let me erase some of this. Let's get it out of the way. And now let's see what happens if we divide a base that's raised to a power by the same base raised to another power. So for this, I'm going to actually use the same exponents that we did initially. Let me just create a separation here so that we have a little bit of space. So now let's see what happens if we do a to the 5th power divided by a squared. And to start with, what I'm going to do is I'm going to make sure that the exponents in the numerator are always larger than the exponent in the denominator. Let's start there, because I think it'll be easier to do and understand if we do that. Okay, well, going back to the definition of exponents, we know that exponents are just repeated multiplication. So a to the 5th means that we have a multiplied by itself 5 times. And we're dividing this by a squared, which is a multiplied by itself twice. Okay, great. Well, what happens here? Well, hopefully we remember how to work with fractions and how to simplify by common factors between the numerator and the denominator. And here we would hopefully remember that we could simplify or cancel out 2 a's. One a in the numerator and denominator and a second a in the numerator and denominator. And in the end, what we would get is just 3 a's, because there is nothing left in the denominator. Technically, the denominator is equal to 1 now, and anything, actually, let me write it down. And anything divided by 1 is just that same thing. So what is a times a times a? Well, another way of writing that is just a cubed. Well, great. Okay, we figured that out by using the definition of exponents. Okay, well, let's try it out with a second example now. Let's do a to the 4th power divided by a squared. Why not? Well, we know what a to the 4th power is. That's a multiplied by itself 4 times. And we're dividing that by a multiplied by itself twice. Okay, again, we can simplify here. These 2 a's can cancel out. These 2 a's can cancel out. And in the end, we are left with a times a. Again, that's divided by 1, because now the denominator is a 1, but we don't need to write it down. We know what that means. And a times a is the same thing as a squared. Okay, let's do one more example. Let's do a to the 7th power divided by a cubed. And again, we know what this means. This is a multiplied by itself 7 times divided by, whoops, I need one more a. And this is being divided by a cubed, which is a multiplied by itself 3 times. We can simplify some of these common factors, and we are left with a times a times a times a, which can be written as a to the 4th power. Awesome. Well, we could continue doing this on and on with different examples. But again, we can ask the question, well, what is, for example, a to the 50th power divided by a to the 15th power? it would be really annoying to have to write out all these a's, then see all the ones that cancel out, and then count how many are left, and then figure out what the new exponent is. Is there a faster way of doing this? Well, this is when we have to use our observational skills and we start hopefully finding a pattern. In this case, the pattern that we might notice is that, well, we're always canceling out however many there are in the denominator. Well, canceling out has to do with reducing, and this idea of reducing and taking away, because we're taking away the number of a's in the denominator from the number of a's in the numerator, this idea of taking away can mathematically be expressed by subtraction. I mean, notice what's happening here. If we subtract 5 minus 2, we get 3. Well, that's the same thing that we got before by canceling out the a's, because we are taking the number of a's in the denominator away from the number of a's in the numerator. If we do the same thing with our second example, well, that would be 4 minus 2, because we're taking away the number of a's in the denominator from the number of a's in the numerator. Well, 4 minus 2 is 2. And again, this matches what we got earlier. Let's try it out with the third example. 7 minus 3, because we're taking away the 3 a's in the denominator from the 7 a's in the numerator. That would give us a to the 4th, which does in fact match what we got before. And we could continue trying out different examples, and we could even formalize this like very meticulously, but from what we have observed, we have every reason to believe that we can always subtract the exponent in the denominator from the exponent in the numerator, and that will give us our new exponent. 50 minus 15 is 35. And we were able to figure that out without having to do all of this long process of writing down the a's in the numerator, writing down the a's in the denominator, canceling out, and then counting how many are left. We were able to do it by noticing patterns. Great, this is awesome. This is fun too. Let's keep playing around, because remember what I said at the beginning of this second section, if you want to call it that way? I made sure that my numerators were always larger than my denominators. And there's a reason for that. Let's look at that now. Let's flip this around and see what happens if the exponents in the numerator are smaller than the exponents in the denominator. So let's look at this. Again, I'm gonna make a separating dotted line so that we can more clearly see the divisions. And now, let's start with the first example. A squared divided by a to the 5th. Okay, again, let's use the definition of exponents. It's repeated multiplication. So the meaning of this is the same as a multiplied by itself twice divided by a multiplied by itself 5 times. And again, we know how fractions work. We know how to simplify them. So here we would simplify these a's, and what we have left is 1 over a times a times a. Interesting. Okay. Well, we know what a times a times a times a is. It's a multiplied by itself 3 times, can be written as a cubed. And awesome, we have our answer. So even when we have an exponent in the numerator that's larger than the exponent in the denominator, we can still use the same the same definition of repeated multiplication to figure out what our answer is. Now, in this case, we do have to write this 1 in the numerator because it's not implied. We can't just write a cubed. So it is important to write that 1. Well, let's continue doing this with our other examples. A squared divided by a fourth. What happens there? Well, a squared is a multiplied by itself twice. A to the fourth is a multiplied by itself 4 times. We cancel out common factors, and we end up with 1 over a times a, which can be written as 1 over a squared. Great, we figured that out as well. Let's do it with another example. A cubed divided by a to the 7th. Again, a cubed means a multiplied by itself 3 times. A to the 7th is a multiplied by itself 7 times. We cancel out common factors, and we end up with 1 over a multiplied by itself 4 times, which can be written as 1 over a to the 4th. Awesome. Well, again, what can we do if we have really large exponents? For example, what in the world would be a to the 15th power divided by a to the 50th power? Well, we already noticed the pattern before. We noticed that we would subtract the exponent in the denominator from the exponent in the numerator. Would this still hold true in this case? Well, if we did that, we would have a to the power of 2 minus 5, which is a to the negative 3. Well, that's a negative number. In fact, specifically, that's a negative exponent. That is a bit weird. Because remember what the definition is. Exponents are repeated multiplication. So we know what a squared is. It's a multiplied by itself 2 times. A to the 5th is a multiplied by itself 5 times. But what is a to the power of negative 3? What does it mean to multiply a by itself negative 3 times? That's really weird. This might not work. This might just be something wrong. Maybe the pattern that we noticed in the previous section only works if the exponent in the numerator is larger than the exponent in the denominator. Because let's look at the second example. Here again, we would have a to the power of 2 minus 4, which is a negative exponent. Here, a to the 3 minus 7, that's a to the power of negative 4. And if we tried to use that pattern with our large exponents in our last written example, then we would have, we'd have a to the 15th minus 50, which would be a to the negative 35. And that's just weird. What is a multiplied by itself negative 35 times? This might not work, like I said. But one thing is a bit curious. Notice that the exponent is always the additive inverse of the power that we figured out by writing down all the a's. Same here. Look at our second example. Negative 2 is the additive inverse of 2. And here again, negative 4 is the additive inverse of 4. So, well, maybe that's something, maybe it isn't. For now, let's leave that there and continue on playing around. So now I'm going to make another division, and we're going to switch gears a little bit. We're going to play around in a different way. I want us to see what happens if we start decreasing the exponent by 1 indefinitely. So let's just start with a to the 4th power and see what happens. So let me write down a to the fourth power. A to the fourth power is a times a times a times a, because it's a multiplied by itself 4 times. Awesome, okay. Well, like I said, let's decrease the exponent by 1. So that would be a cubed. So we're decreasing the exponent by 1. Well, a cubed is a multiplied by itself 3 times. So that's a times a times a. Okay, nothing special so far. Let's decrease the exponent by 1 again. That's a squared. So we're decreasing exponent by 1. That's a times a. Let's do it one more time. A to the power of 1. So we're decreasing the exponent by 1. And that is just a. Well, that's already something interesting, actually, because now we have a way of writing an exponent for a single a. You see, before, when we wrote a single a, okay, well, we didn't necessarily know what that meant. But now, if we're following this pattern of subtracting the exponent by 1, we realize, oh, okay, this makes sense. A multiplied by itself once is just a. So a to the power of 1 is a. So anything to the power of 1 is itself. Interesting. Okay, well, let's subtract one more time. Well, here we're getting into territory that is a bit weird again. If exponents are repeated multiplication, then what does it mean to have an exponent of 0? What does it mean to have a to the power of 0? A multiplied by itself 0 times. What in the world could that mean? Well, if we continue the pattern that we have, we might get an answer to that. Now, for that, we need to actually understand what's happening from one step to the next here. Now, we know what's happening on the right side. We're subtracting the exponent by 1. But what's happening on the left side of these equations? Well, we are actually dividing by a. So to get from the first line to the second line, we are dividing by a. See, that's how one of the a's cancels out and we get the next line. To get from the second line to the third line, we have 3 a's multiplying themselves, and we divided by a, and that's how we got a squared. Now, to get to the next line, we just continue with the same pattern. We're dividing by a, which means that maybe if we divide by a one more time, we can get an idea of what a to the 0 power might be. Well, to do that, we would have to divide a by a. And that means that the 2 a's cancel out, and a divided by a is just 1. Well, this is again a really cool discovery. We clearly have a pattern here. It didn't necessarily make sense to talk about a being multiplied by itself 0 times, but according to this pattern, a raised to the 0 power is equal to 1. That's not self-evident, but this is in fact a true statement. After many years of playing around, many centuries of playing around and seeing if this statement holds true, it is in fact true. Now, I actually forgot to mention the names of some of these things that we are discovering here, but this first statement in the purple box is actually the property of exponent 1. And And by following this pattern, we actually discovered the property of exponent 0. And the property of exponent 0 actually says that anything to the power of 0 is equal to 1. So anything to the power of 0, anything, no matter what it is, it could be an elephant raised to the power of 0, and that is equal to 1. Well, why stop there? Why don't we continue subtracting 1 from our exponent? Well, if we subtract 1 from 0, that's negative 1. Ooh, see, here we get into strange territory again, because we already saw some negative exponents before, and we didn't quite know what to do with it. We didn't know if it actually made sense. Well, here we have negative exponents again. Let's see what happens. We already said that the pattern here is dividing by a. So we have 1. What happens if we divide by a? Well, nothing cancels out because 1 and a don't have any factors in common. So we would just write 1 over a. Okay? Let's decrease the exponent by 1 again. Well, that would be a to the power of negative 2. If we continue the pattern, we would have to do 1 over a divided by a again. Well, hopefully you remember how to work with fractions. Now, this can be rewritten in a couple of different ways, but hopefully you would understand that this complex fraction is the same thing as 1/2 multiplied by the reciprocal of what you're dividing by. So that would be times 1 over a, because the reciprocal of a is 1 over a. Well, 1 over a times 1 over a is 1a squared. Now, another way that you can think of this is down here. We could write 1 over a divided by a. You could use the concept of equivalent fractions, and we could multiply both numerator and denominator by a, and we're allowed to do that because this fraction is just equal to 1, and we can always multiply by 1. Well, here the a's would cancel and we have 1 left, and down here a times a is a squared. So no matter how you want to think of it, the simplified version of 1 over a divided by a is 1a squared. So let me quickly erase all of this. And now we can write that it is equal to 1 over a squared. If we continue on, this would be equal to 1 over a cubed. Well, I don't know if you remember what we had before, the results that we got in what we could call the third section, but let me show it to you. Look at this. We had gotten that a to the negative 3 maybe meant 1 over a cubed. Well, that's exactly what we just got here. That a to the negative 3 is equal to 1 over a cubed. Look at what we got for a to the negative 2. We get that it's 1 over a squared. That's exactly what we got up here. A to the negative 2, we got that was 1 over a squared. Well, back when we first looked at this, I mentioned that it was weird and that maybe it was that the rule broke down. Maybe the pattern that we noticed didn't work when the exponent in the numerator was smaller than the one in the denominator. But we just got the same exact result with a completely different method. This lends weight and it lends credence to the fact that, okay, maybe this is actually true. Maybe this is the pattern that we see. And like I mentioned before, over the course of many, many years, this is what was discovered. The discovery was that, in fact, negative exponents are the reciprocals. They are the reciprocals with the positive exponents. So we can actually write down the property of negative exponents, which says that anything to a negative exponent is equal to its reciprocal with the exponent being positive. Great. So now we actually have several properties of exponents. We have the property of exponent 1. We have the property of exponent 0. We now know what negative exponents are. At the beginning, we also discovered the product property. And now that we actually know that our pattern here is valid even when it gives us negative exponents, we can now write the quotient property. Quotient means division, just like product means multiplication. So the quotient property can be written as a base to a power divided by a base to another power. That same base, sorry, that's important. It has to be the same base. Well, we can quickly figure out what the new exponent is by subtracting the exponent in the denominator from the exponent in the numerator. There you go. Okay, let me make a little bit more space by erasing some of these properties, because we do have some more exploring to do. I'm going to make a dotted line again so we can have some separated space. And now I want us to see what might it mean if we raise something that has an exponent to another power. So let me write down an example. A cubed to the power of 2. Well, we can use the definition of exponents to figure this out. Exponents are repeated multiplication. So if we have a cubed to the power of 2, it means that we have a cubed multiplied by itself twice. Well, we can write that down as a cubed times a cubed. Okay? We could again use the definition of exponents to make sense of this. This is a times a times a, because a cubed is a multiplied by itself 3 times. And that's being multiplied by a times a times a. In total, we have 6 a's, which means that we can rewrite this as a to the power of 6. Now, I do realize that we already know a property that would allow us to figure this out quickly, but let's just, for the sake of this example, or this exploration, I should say, leave it written out. What about a to the 4th to the power of 3? Well, the meaning of this is that we have a to the 4th power multiplied by itself 3 times. So let's write that down. There. A to the 4th multiplied by itself 3 times. We can again write out all of this in terms of a by remembering that a to the 4th is a times a times a times a. meaning a multiplied by itself 4 times, and then again with the other 2a to the 4th powers. In total, what we have here is a multiplied by itself 12 times. And we can continue this over and over and over again with a ton of examples. But again, we should ask ourselves, well, what if we have larger exponents? It would be very annoying to have to write all this out. Even if we decide to use the property of the product property of exponents, which we already know about, that would make it a little bit easier, but maybe there's another pattern that we could identify here. Well, here in the first example, a cubed is the same thing as a times a times a. A cubed is a times a times a. In the second example, a to the 4th is a multiplied by itself 4 times. The next a to the 4th is there, and the third a to the 4th is there. Well, with enough thinking, we would hopefully notice, let me make a little bit of space here. I'm going to bring this down. Hopefully we would notice, well, wait a minute. Here we always end up multiplying groups of the same size. See, down here we're multiplying 3 groups of 4 A's. In the first example, we're multiplying 2 groups of 3 A's. Well, any time that we are adding the same amount of groups or adding together the same amount of numbers, that's called repeated addition. Repeated addition, because we're adding the same number over and over again. And man, hopefully this made it click for you. Repeated addition is the same thing as multiplication. Repeated addition is the same thing as multiplication. Well, what is it that we're multiplying? We are multiplying, in the first example, we're multiplying 2 groups of 3. That's 2 times 3. In the second example, we're multiplying 3 groups of 4. And the more examples that we find, we would notice, wait, these numbers that we're multiplying are the same as the exponents. And that is, in fact, where the property of a power to a power comes in. Let me write that down. Power to a power property. And this property tells us that if we raise a power to another power, we can figure out the new exponent by just multiplying the exponents. That's the power of a power property. Or power to a power property, power of a power property. Any name that expresses the idea would be sufficient. Awesome. Let's make a little bit more space again. And here we are getting to the end of our exploration. Now, really, there are only a couple of other properties that we have to discover. 3, in fact. Today, in this video, we are going to just look at 2 more. The last property of exponents we're going to leave for another time. So the last little bit of exploration that we're going to do is by seeing what happens if we raise a product to a power. So for example, what happens if we have a times b, which is a product. Product is a multiplication. And we raise that to the power of 2, for example. Okay, well, let's write this out using the definition of exponents. A times b to the power of 2 means that we are multiplying a times b by itself twice. So a times b multiplied by itself twice. So a times b times a times b. Okay, well, what if we have ab to the power of 3? That would be a times b multiplied by itself 3 times. We can write that as a times b times a times b times the third a times b. If we did this to the 4th power, that's a times b times a second a times b times a third a times b times a fourth, times a fourth a times b. Awesome. Okay, well, that looks a little bit unorganized. Let's organize this a little bit. In the first example, a times b times a times b can be written as a times b times b. So we can organize this by variable. Organize this by variable. And the reason we can do this is because of the commutative property of multiplication, which essentially says that you can move all the factors around however you want. Just think about this. 2 times 3 is the same thing as 3 times 2. The order in which you write down the numbers doesn't affect the value. 2 times 3 is 6, 3 times 2 is also 6. The order in which you write the factors doesn't matter. Well, that's always true. So that's why we were able to reorganize these variables so that they look a little bit more organized. In our second example, we could write this as a times a times a times b times b times b. And finally, down here, a times a times a times a times b times b times b times b. Well, all of this has a ton of repeated multiplication, so why don't we just write it with exponents? A cubed times b cubed, and down here, I'll write it down here, a to the 4th times b to the 4th. Awesome. And we could do this with a ton of examples, but in the end, if we are careful about noticing any patterns, we would hopefully realize, wait a minute, all that's happening is that the exponent that we raised the initial expression to, now all of the factors inside of that expression have that same exponent. So this is almost like the exponent goes to each individual factor. I say almost, but that is what's happening. You can almost think of it as distributing the exponent, although it's not quite like that. As you can see, it's just as we rewrite the expressions using the definition of exponents, we end up noticing the pattern that in the end, each factor in the original expression gets raised to that exact same exponent. So this, in fact, leads us to the power of a product property. Power of a product property. It's just saying that we are raising a product, a multiplication, to a power. And, I mean, we already said it in words, but normally this is written something like this, where each factor receives the same exponent. And we can actually do this with division as well, with a quotient. So let me make a little bit more space. Let me erase this. Eliminate. Make a dotted line. What if we have a division raised to the second power? Well, same kind of idea. We multiply the quotient by itself 2 times, and then use exponents. Actually, here, let me clarify this here. And just remember what multiplying fractions is like. We multiply the numerators and we multiply the denominators. And now we can rewrite the repeated multiplication with exponents. If we do this to the third power, same kind of idea. We multiply the quotient by itself 3 times. We can write it as a single fraction because we multiply the numerators and we multiply the denominators. We rewrite the repeated multiplication as exponents, and with a little bit of observation, we again realize that the exponent gets almost like it's getting distributed to the numerator and the denominator. And this would be called the quotient property, where essentially any quotient raised to a power means that the numerator, the whole numerator, gets raised to that power, and the whole denominator gets raised to that power as well. And again, that's called the quotient property of exponents. Hopefully with this exploration, you're able to see or get a taste of what happened throughout centuries of work, what different mathematicians did throughout different decades and centuries, and how it all came together eventually to what we now call the properties of exponents. Now you know where they came from, and now it's time to learn how to use them.